As you guess, I'm not a code developer. I mean, I am, but I'm not a software engineer or anything like most folks here. I'm actually an astrophysics professor in academics. So I'm an academic. My job is to do research in relativistic astrophysics and teach classes, I guess, to my students. The reason I'm here, I guess, is that I try to be an astrophysics professor that is mindful that good discoveries and modern scientific discoveries are actually done with excellent software. So the story, I guess for this audience, so at PyCon or so, I hope this will be a deep dive into a specific domain that maybe you know, maybe you don't, which is that of gravitational waves and black holes, where good software is, and I will try to argue, Python is actually the deep secret behind the discoveries that we make. I can actually, this could be maybe a domain of interest application for the beautiful code that you guys write. All right, so this is 2 words really about, this is not working, okay. 2 words about myself really. So I graduated, I'm actually from the Milan area, I graduated over there. Then I got my PhD in applied math in Cambridge. Then I had a couple of research positions around. I went to Caltech in Pasadena, California, then back to the UK in Birmingham, and then I landed on the faculty at Milano Bicocca, where I'm from. Again, the things I do, I lead a research program in relativistic astrophysics. Again, try and discover black holes and gravitational waves, which is what I want to talk about today, with prominent ERC, European Research Council support. I'm now leading a group of about 14 people. I have a prominent teaching activities. These days, professors got to teach. So researchers have to teach. And my teaching actually portfolio is all on astrostatistics and scientific computing with Python and so on for a physics department though. So it's all applied, applied computing. Again, all I do is done in Python, and that's the reason why I wanted to connect with the audience here. All right, so let's start from the beginning in astronomy, I guess. What do we know about the universe? And if you think about it just for a tiny second, the answer is a lot. From the smallest scales, like the planet, I guess we live on one, the stars, we see stars around where the sky is not too polluted. These stars are bunched up in galaxies. So each of these galaxies, including our own Milky Way, has order of 100 billion stars, 10 to the 11 stars in a thing like this. This picture here is the deepest image ever taken of our universe, and each of these little dots is a galaxy. So each of these little dots has 100 billion stars, probably with order 10 planets each around, right? So really the vastity of the thing that we are uncovering is immense. And if you think about how we know all of this, we only see one thing, which is light. So all these objects and beautiful things that the universe does for us, they emit light, and that's what we measure. That's the messenger that we use to actually discover everything. Now, the universe, it's not kept together by light, but rather by gravity. So it's the gravitational force that keeps the universe together, but we see a very indirect byproduct of this, which is the light that stuff emit. Now, the challenge of doing gravitational astronomy now becomes, can we actually use gravity? Can we use gravity itself to discover something about the universe? And this is really the questions that I face in my own research activity, I guess. So to start going into this brings you back, I don't know, to high school, I guess. But, if you remember Newton's law, right, that says that if you got 2 masses, say the sun and the earth, little m and big M, the force between the two goes as, I guess this works, goes as the 2 masses, proportional to the 2 masses, that goes down as 1 over the square of the distance between the two. You massage this equation a bit, again, this goes back to, I guess, 3rd year high school or first year university or so, and you find Kepler's law. That says that the square of the period, so this is 1 year for the Earth, that the little mass takes to go around the big mass, the square of these goes as the cube of the separation, right? Now, these laws is beautiful and actually explain all the planets in the solar system spectacularly. It has some deep unsatisfactory, something that is deeply unsatisfactory, and there are 2 things, right? So the Earth, right, the period of the Earth, this is 1 year, needs to know the mass of the sun, big M. How is that possible? How does the Earth know how fast should it go to complete a revolution in 1 year according to this law? And also, we can make a thought experiment that I hope it doesn't happen, but suppose that the sun blows up, like instantaneously, right? this thing says that magically the Earth now should follow another trajectory. Or suppose that the mass of the sun doubles, like instantaneously, for whatever weird reason, right? Now, if the mass of the sun doubles, the period of the Earth should go down by a factor of 4. How does the Earth know? What's carrying the information from the sun to the Earth that say, hey, you now should speed up? Now, all of this is completely absent in Newton's law that dates back to the 1700s, right? So there's something really unsatisfactory here that tells us that this is not really what gravity is. So what is the messenger of gravity in other ways, right? This is deeply connected with something else that Newton did that again probably brings you back to high school or so, which is that Newton not only figured out the laws of gravity here, but also that any force F is related to the acceleration that the body has, proportional to the mass itself. This is the famous Newton's second law, right? Now, very easy. If you just plug these two together, I mean, if you have a system where there's only gravity, you arrive to this thing. That's standard, super trivial, this little m simplifies, right? Now, this is, again, hides some very deep insights in here, which is actually what Einstein really was curious about, right? Which says that, well, the little mass goes away, right? So I can always get away with gravity. So gravity, I can only think that gravity is not there, but that there's really an acceleration. So think about a thought, let's do another thought experiment. And by the way, these are, well, okay, later. Let's do another thought experiment, which is you're in an elevator, right? An elevator on Earth, and so gravity is really there, right? You're building in your house or so, right? Now, you're going down, and then at some point, the rope of the elevator snaps, and you're falling down, right? So you're about to die, but you have time to think about gravity and physics and what's not, right? And think about what happened to the guy next to you and the guy next to you, who's also about to die, but also thinking about physics, so you're having lots of fun. So the guy next to you, in an elevator that is falling down, you can imagine you will be floating, right? Hope this is kind of makes sense, right? Now, what happens to the astronaut on the space station? Or now imagine you have an elevator in deep space that is floating around in deep space with clearly no gravity, right? What the guy next to you and you are doing, you're really floating. Now, if you now imagine waking up in a box and the guy next to you is floating, you really have no way to tell whether you're in an elevator that is about to fall down and you're about to die, or you're free floating in deep space. You're probably about to die as well in that case. But okay. But what I want to say is that there's really no way for you to tell whether gravity is there or not. Right? So this thing is called the equivalence principle, and was actually motivated Einstein to reshape the entire field of gravitational physics. These are snapshots from Inception, if you ever seen the movie. It's an amazing movie, which has really accurate gravity in there. So this is a sci-fi movie where they go into dreams, and then it's the dream of the dream, and so on, right? And there's one dream level where they're in a van that is falling down a bridge, and in the level below, gravity disappears. That's exactly Einstein's equivalence principle at play, which was pretty cool to see. All right, so Einstein comes along and said, because of all these deep reasons, gravity cannot really be a force. It needs to be something else. And his interpretation now, which is mind-blowing still for the time, but also now, is that gravity is actually curvature of space and time, actually. So you can imagine doing the following thing. Suppose that you have a ball, right? And I let the ball go. Now this ball will go straight. And straight motion means there's no force attached to it, right? Now suppose that now you have a surface like this. If you throw a ball straight, that straight in a surface will actually mean curved, right? So if I throw a ball without any additional force in a curved surface like this, the ball will actually go around. Now Einstein's interpretation is that there's something, which is the space-time, that it's bent by the presence of a mass. So the sun here bends the space-time, and then all the Earth does is following the straight line in a curved space-time. So gravity disappears. It's not an extra force, a magical thing that goes between here and there, but it's just inertia in a curved space-time. And that's the logical step that you have to take, right? And when Einstein proposed this, that was the early 1900s, that was totally crazy, and it still is, right? I mean, it's still kind of, So, okay, sure, right? There's a giant rubber sheet and whatever, what do data actually say? And this is actually where Einstein fames come from, which is the 1919 eclipse. Because if this business, oh, now it works. If this business is true, that means that not only masses, say, the Earth, but also light. At that point, light goes straight, and straight now means something else, so also light should be curved by the presence of space-time, which is something completely absent in, say, Newton's theory, where instead light just goes straight, right? So what they did, what they set up to do in 1919, led by Eddington, a famous British astrophysicist at the time, is to go all the way to where they had two sites, one in South America and one in Africa, to measure a solar eclipse. So the idea is that if you have stars, so lights of stars, that they pass very close to the sun, if all of this business is true, their passage is so close to the sun, they should be slightly bent. And so by measuring these deviations, that would be a test of Einstein's theory. Now, the problem is that you never see stars that are close to the sun, because the sun is super bright, right? So the only way to do it was to actually wait for a total solar eclipse and hope that some of the little stars that are visually in the path of the sun, so the sun now disappears, I mean, the moon gets in front, and then you can measure tiny deviations and so on, which is what they set up to do. And this is the actual original plate, which confirmed the theory in a spectacular fashion. And that's actually, this experiment is actually where Einstein's fame of the mad scientist with gray hair and whatever, this is actually how he got super worldwide famous, right? Right, so now, by now, Einstein's general relativity, how we call it, is the default explanation for all gravitational phenomena. And here is a bunch of big actors in the field, really. So from Schwarzschild, that described the first black hole, as we call it, Wheeler, that then popularized it after the war, Kip Thorne, who was a student of Wheeler, and was actually the leader of what I'm going to talk about in a second, which is the effort to actually detect the messengers of gravity. Jocelyn Bell discovered the first pulsars, which is a specific kind of star. This is extremely useful to test the theory itself. Kerr wrote the first rotating black hole solution, and all the way to Stephen Hawking, which is also did immense development on the theories of black holes and so on. Now, one of the key, I've been saying the words black holes a lot now. One of the key predictions of general relativity is that there could exist, potentially, regions of space-time that are so compact that not even light can escape, right? And this is the toy model here could be, suppose that you throw a ball up. If I throw something up, this will come down. If I throw it up quickly enough, say a rocket, this would leave the gravitational field of the Earth. In a black hole, nothing can escape, not even light, right? Before collapse to a black hole, what can happen is a neutron star, which is basically a star collapsing and reaching density which are close to nuclear density. Basically a giant nucleus of about 10 kilometers, right? Now, then we go back to so if I go back to my astrophysics friend, they will actually tell me that now black holes and neutron stars are well understood. They are the natural graveyard of stars. So modern stellar theory predicts that stars, as they end their lives, they eventually end up in these funny solutions, which are black holes and neutron stars. So in a nutshell, the life of a star, so the sun exists there are two things going on in the sun. There's gravity that tends to collapse the sun, and then the nuclear reaction that keeps the sun up. The pressure from the nuclear reaction that keeps the sun alive. Now, at some point, the nuclear fuel, the sun right now is burning hydrogen, will finish, and then the sun will collapse a bit, eating up, reaching the ignition temperature of helium, it will start burning helium, and so on and so forth, until there's nothing left to burn. And depending on the mass of the star, so how much material is left, the whole system collapses either to a neutron star or to a black hole. So those things that were predicted by theoretical physicists thinking about the nature of gravity and so on are now well understood in the astrophysical landscape. And we think that basically all stars or most stars will actually go there eventually. Right, then next step, what happens if I put two of these guys together, right? Say you have two of these fantastic black holes put together. Now they will, imagine the rubber sheet that we had before, they will perturb this rubber sheet, much like when you drop a stone in a pond or so, right? These perturbations, right, they are called gravitational waves. So these things will eventually propagate outwards. And this propagation carries out energies, right? Much like when you shake something, the effort that you have to put is the energy that goes away. Now, if you dissipate energy, again, Newton tells us that the binary has to shrink a little bit. So it needs to settle on a lower energy level because some of the energy is being gone. So the orbit must shrink. Now, must shrink, shrink, and shrink. Eventually, these two black holes will merge. So these cosmic collisions is one of the most energetic events in the universe, right? And they're actually deeply predicted by all this beautiful theory, if it's true. The first confirmation of all this business that looks crazy came in the 90s. So these are not really black holes, these are pulsars. So these are rotating neutron stars that happen to emit radio waves in a very collimated fashion, much like lighthouses. So every time the pulsars rotate, it's like a lighthouse that sweeps in front of our telescopes. And so we can time how quickly the pulsars are going around each other. And what we are seeing is that they're speeding up. They're going around faster and faster and faster. And their prediction is precisely what's predicted by Einstein. And this is a Nobel Prize plot, that on a baseline of like 30 years or so, these are measurements with error bars, and this is the theoretical prediction. And this is not a fit. This is not a machine learning fit or whatever. These are the theory, right? This is Einstein's equation at play, right? So which is just amazing, right? All right, so let's try and do, sorry, there's probably one only slide with math, but let's do some order of magnitude calculations here, right? So the net effect, so the phenomenology of this problem is the following, right? If you have a ring of masses like this, if you have a gravitational waves that hit the ring of masses, these will oscillate in this fashion, right? So how big these things are, just to figure out whether we can hope to detect them, right? So if you have a detector of size L and a strain, meaning the intensity of the gravitational wave of size h, you can measure h provided that you measure your detector with the precision delta L. So a gravitational wave measurement is essentially measuring your detector extremely well. So you need to know, if you know this length here, you need to know how much is variating. You need to be able to measure how much is variating. So the resolution that you need, delta L, is about L times h, where L is the size of your detector. This immediately tells you that you want big things. You want a big detector, right? Not something small. Now, the emission from the source point of view goes as the mass, the velocity square, and the distance. Now, let's put some number through this, right? So suppose that you have, I don't know, 2 cars, 1 ton each, going at 1,000 kilometers per hour. That's a lot, so 2 fast cars. And I place my detector as close as possible, which is 1 wavelength away, which turns out to be of the order of the radius of the Earth. If you put these things together, this strain that you get is order of 10 to the minus 42. That means you need to know your detector with a precision of 10 to the minus 42, which is just completely crazy, right? Now, okay, let's play with binary black holes, which is where I actually want to go. So these guys are, say, the mass of 10 times the mass of our sun, 10 to the 31 kilos. At the end of their life, they can be quite fast, say 10% of the speed of light. And let's put them close to the closest galaxies that we have, about 100 megaparsec or so, which is, well, okay, not the closest galaxy, so the closest cluster of galaxies, which is farther away. So I'm more conservative here. You put these numbers together, and you find 10 to the minus 21, which is still a crazy small number, right? So if you have a detector of a size 1 kilometer, 10 to the minus 21 kilometer is less than the size of a proton, right? So that means knowing the size of your detector with the precision that is less than that of a single proton. And that's the kind of engineering challenge that it's at play. So the signal that we are looking for actually looks like this. So what the black holes are doing is that the two of them are ring spiraling, we say, going around each other, emitting energy in gravitational waves, and these are the energy that eventually reaches our detector. Then the two black holes will merge, basically collide, and that's where they emit most of the energy, and so where our signal will be larger. And then there's this, we call it a ring down phase, where the system settles down, right, quietly. Now, this is the signal we're after. The way the signal actually looks for is like this. So we're looking for a tiny, tiny thing swamped in noise that is many, many, many orders of magnitude larger than that. So you can imagine this is an immense, immensely challenging pattern recognition problem, essentially, right? And all right, so, well, we need a precision of 10 to the minus 21, which is just, no, this is never going to work, right? So people started pioneering detectors for these kind of things all the way back to the 60s. So this is the first attempt by Weber, a physicist in Maryland, and his idea was to grab a giant bar of aluminum and then put these detectors, these materials that convert physical vibration into electric signals. And then the idea is that the gravitational wave hits, the bar vibrates, and then you detect the signal also. Great attempt. Right now, I mean, these techniques don't really work to the precision that we need. The modern technique is that of using laser interferometer. So now the challenge, the setup is that you have a laser here that's divided by some semi-reflecting surface. Half of the power goes down or goes up, half of the power goes here, two mirrors there, they reflect and they recombine. Now, if the two lengths of the two arms of the interferometer are identical, what you get at the end is exactly what you've emitted. If they're not, because a gravitation wave has been hitting in, has been distorting the whole thing, what you get here is different than what you've emitted. Now, the secret is that I use the wavelength of the laser, nanometers, to make a measure, so to increase my resolution massively. That's the key experimental secret. Now, these things that we use are big. So these are the current detectors on Google Maps. You actually see them on Google Maps. They're 4 kilometers in scale. There are two machines in the United States, one in Louisiana and one in Washington State. And the European antenna is actually here in Italy, close to Pisa, called Virgo. So yeah, these are the arms of the interferometers, right? So there's a laser source here that travels all the way 4 kilometers down here, a reflecting mirror, and it's recombined at the central station. These are some pictures of the LIGO machines, which is, again, it's an immense feat of engineering, right? The level that these machines achieve is, again, measuring the size of their detector, 4 kilometers, with a precision that is less than the width of a single proton, and which is just mind-blowing, right? I'm not an experimental physicist, unfortunately, but I find this immensely fascinating. Right, so the story begins, and by the way, this plot was done in Python, clearly, right? This is a Nobel Prize plot, right? The story begins in, so 10 years ago, 2015, September, day 14, where the two LIGO detectors detected this. So there's some noise here, some noisy signal here, and then these 4 cycles, which are coincident between the two detectors. That's the whole point of building 2 detectors, is that this measurement is so hard that you'll never believe it if only one detector sees it, because, I don't know, something vibrates in the whatever, right? So, but 2 detectors seeing the same 4 cycles coincidentally, that was amazing, right? And the actual typical thing that we look for are these kind of things. So this is time, and this is frequency, and this specific shape, which goes as time to the 8/3, is actually what predicted by general relativity, by Einstein's general relativity. And the detection problem here is essentially pattern recognition on these kind of maps, right? We look for chirps, we call them, so signals that look like this with this specific power to claim a discovery, right? So this was 2015, and since then, the field has exploded. Now, these are sky location in the sky. So a gravitation wave detector is not really like a telescope or whatever. You don't point it to anywhere, right? It's more like a microphone that stays there and sits and listens to whatever happens. The fact that we have multiple detectors lets us like triangulate and figure out where the signal is coming from. So these are the area in the sky that we could pinpoint our signal as coming from, right? And this is what happens when we're only 2 detectors at play. Then a few years later, the European antenna came online, and this region shrank by a lot. Right? These are now the typical sky location with 3 detectors operating. And the reason is that there's an extra triangulation point, and 3 from 2 is a massive improvement. And right now we have more than 90 or so observations of this. Actually, almost 100, more than 100 now. 90 have been published so far. But right. So the next big discovery that happened was in 2017, where the LIGO saw one of these chirps, much longer than the other one. So the previous one were about a millisecond. These are about 10 seconds, so much longer. The reason is that these are lower mass sources that emit for longer. Namely, these are neutron stars, the giant nucleus that I was talking about before. When you smash 2 giant nuclei together, you can imagine that not only gravitational waves come up, but all sorts of electromagnetic phenomena and so on. So when LIGO saw this, then immediately, essentially that night, all telescopes on Earth started pointing at that location in the sky to see what was going on right there. And well, 14 seconds after, the first telescope saw a burst of signal. These are gamma rays, which are extremely energetic photons. And then some 10 hours later, essentially where that region in the sky became visible from Chile, which is where most of the telescopes are, telescopes started scanning the sky and found this. So there's so these are archival so these are archival images where you see there's No, it's a galaxy like many others. And then these things happen. So this little dot here that you see in these many telescopes that have observed, this is a new source. And it's not coincident, it's timely and spatially correlated with the gravitational wave detector. So this is the next level. This is the same signal that we are observing in both light and gravity, which is really next frontier here. And that's happening in 2017. Yeah, so I can skip this. And for the decisive contribution to the light detector and the observation of gravitational waves, Ray Weiss, Barry Barish, and Kip Thorne, same guy, a few years older, that we had in the picture before, got the Nobel Prize in physics in 2017. And this is a kind of a personal note, but at the time I was a first year, I guess, postdoc at Caltech, and I ended up, so the news of the Nobel Prize came, well, it was in Stockholm, so we figured out when it was early morning in California, and I was walking to work, and I bumped into the Nobel Prize, party here. These are the folks getting a Nobel Prize, and that's me in the back. And this is so on that day, my hometown, I'm from Monza, north of Milan. My hometown's newspaper actually published this because my high school friend put this on a social media with an arrow next to my head or something. I was literally, it was 7 a.m., 8 a.m. or whatever, and I was walking to work on this day. All right, so more on the data analysis side of things. I'm actually a gravitational wave data analyst, more than an experimentalist or a theorist. So there are 3 levels. There's a 3-layered cake here that we're dealing with. So first, LIGO, say, takes a year of crap. So it takes a year of data, and we are interested in a few milliseconds. So the first challenge is to locate that interesting bit that matches that chirp that we saw before, which is completely dominated by noise. So that's a deep mining operation, if you want. Then, once that millisecond has been identified, we need to look deeper into this to measure properties, say the masses of those black holes, the orientation, where it was in the sky or so. We call this parameter estimation, which is basically dig deep in that, and we use Bayesian statistics for doing it, in that millisecond to figure out the properties of the sources. And then, which is actually closer to my own research field, is what we call gravitational wave populations, which is, now that I've measured 100 black holes, what's the global spectrum of black holes in the universe? And the data analysis problem here is that to infer the bulk properties of sources, given individual noisy measurements, which are heavily selection biased, because our detector is not equally sensitive anywhere. And, oh well, the deep secret behind all of this is Python, to some extent at least, right? Not to some extent, I actually mean it, right? There probably won't be, all the plots that I've seen were done in Matplotlib, right? Or Seaborn or whatever, right? So there probably won't be Nobel Prize, or at least not that quickly, without Python. Now, these days we use it for data accessing, so where the way our data are stored, searches, so looking for that interesting millisecond. Bayesian sampling, we are, in the gravitational wave world, we are convinced Bayesians for our stats. And actually, some prominent samplers in Bayesian statistics were actually developed for gravitational wave science and then outsourced and exploited in other fields and made general. Even for compiled legacy code, these days, all the interfaces that we use are written in Python. And it's not an overestimate to say that basically every PhD student in my research field graduates with a Python package on pip, right? So their sign in the field is not only put a paper out, but also make something pip installable and put a GitHub hash on their CVs and so on, right? So we are toy, I guess, engineers, software engineers, like, not like you guys. The code that we write is crap compared to yours, right? But because we spend time studying physics, I guess, right? But I have to say that I try to get, and the reason why I signed up for this conference, right? I have to say that my research field in the last 10 years or so has seen, since I was a PhD student for sure, has seen a massive move towards open sourcing and so on. Again, now putting out packages is careers for our PhD students as well. There have been Kaggle competitions on gravitational waves, and big experiments like LIGO and Virgo and so on now include software engineers from the ground up. When they plan the experiment, they are aware that without good stuff going on under the hood, there won't be Nobel Prizes and big discoveries, right? So these are some of the things these days you can pip install in gravitational wave if you want. So GWPy is our main access to gravitational wave data. That's the raw strain data that comes out of the detector. GWOSC is an open source archive where you can actually go and download the individual pre-processed data. GWFast was actually written by a collaborator of mine with some contribution by myself. This is to do prediction for future detectors that don't exist yet. GW population is to put events together in Bayesian statistics. The black hole perturbation toolkit, that's to study black holes and how they're perturbed by small deviations or so on, which is the end of our gravitation wave signals. Surfing black holes, that models the final black hole that comes out of a merger from the previous black hole. It's a Gaussian process regressor that we wrote with the student and other folk. PopStock is stochastic gravitation wave background. So when you have many sources overlapping, we use it for outreach. So these GW apps is public engagement. These are public engagement tools. PyCBC, that's a tool for pattern recognition of this chirp that I was saying before. Bilby is a Bayesian sampler. It's a nested sampling algorithm that was developed by gravitation wave people and tailored to our problem. Dingo, which is the new version of Bilby. Bilby is an Australian animal, and dingoes eat Bilby. So there's a competing code. So that's a different code. So Bilby was written by an Australian code. Now, some British folks, they wrote Dingo as a new sampler that is supposed to, and they use simulation-based inference. So the field is moving towards machine learning as everything else, I guess, these days. PyRing is to study the end of the signal. We have Icaro, we have Inferno, Asimov. Precession is my own, by the way. So this is something I wrote to study the dynamics of spinning black holes in particular. So really, these things are really deep in what we do, right? And our students, our self-led researchers, or so on, 90% of our time is in front of a Jupyter notebook, or maybe engineers don't like notebooks, but code that is well documented and linted and whatever. Sorry. All right. So gravitational waves are really a new window on the universe, right? So this is the Andromeda galaxy, which is the closest galaxies to us, in different wavelength of the electromagnetic spectrum, right? This is what you see if you were to have radio goggles, right? This is what you see if you were to have infrared goggles. These are low mass stars that emit in the infrared. This is the visible light. So if you have very powerful telescope, that's kind of what you see. In X-ray, you see isolated sources. Now, gravitational waves are a completely new way. So we like to think of this as a completely fundamentally new window on the universe, a new way to look at what's around us, right? And we've seen merging black holes, but now the challenge and actually the excitement in the field is to expect the unexpected. So sources that emit gravitational waves that we don't know already what they are, like black holes. If you want, let me close with almost close with an analogy, which is listening to the universe. So if you look at this picture here, you know what they're doing, right? They're playing. You recognize the instrument and so on, but if you ask you what are they playing, you don't really know. Is this Mozart? Is this, I don't know, Beethoven, the soundtrack of Star Wars? Or, you don't really know, right? So that's the key act that they're doing. It's unknown to you. Their key goal, which is playing Mozart or whatever, it's unknown. And that's what the universe kind of is to us. Right? We observe light. A universe that is kept together by gravity, we observe light indirectly. And gravitational waves are the hope and the promise of actually listening to and not just looking at the mute orchestra. So much like light as wavelengths, so we go from radio wavelengths where the wavelength is the size of a building, all the way to gamma rays, which are the size of a single atomic nuclei, the visible light somewhere in between. At the same, exactly the same fashion, gravitational waves have a spectrum and frequencies. And all we've done so far is to measure stuff here at around 100 Hertz. That's where our ground-based detector, like LIGO, observe things. But the spectrum of gravitational wave is big and wide. And there are experimental ideas and prospects for broadening the windows on our universe, most notably in the millihertz regime around here and down all the way to nanohertz frequencies. And so these are three things. At 100 Hertz, you need a ground-based detector. So you need two lasers in the ground. At a millihertz, right here, the frequencies are smaller, the wavelengths are larger, you need a bigger detector. How big? Millions of kilometers. We don't put millions of kilometers on Earth, we go to space. And that's the idea of the LISA space mission, which is a space mission proposed and now approved by the European Space Agency to observe gravitational waves from space. It's going to be 3 satellites separated by millions of kilometers apart with lasers connecting them, shining lasers one on top of the other, such that then the relative position of the satellite tells you about the passage of gravitational waves. All the way to the nanohertz regime, here the distances that you need becomes astronomical. And the strategy then becomes to use pulsars, those pulsating neutron stars, time many of them, and see how their correlations between time of arrivals deviates by what you expect. And this business is called pulsar timing array, and has the promise, and they also have a tentative detection actually these days. It's still unclear what their noise sources are and so on, but they have a tentative detection of a background of gravitational waves all the way down to the nanohertz. And really, I'm done. These are some bigger picture of this same thing. Just to say that, well, I'll skip this. This is LISA. So it's the same diagram as before, which is a partnership between ESA and NASA, and it's going to be the next revolution in my research field. The date for launch is, we hope, 2034. Well, no, it's been planned. This thing is, they started planning it in the 90s, right? So the time for space mission is immense, right? So the amount of, well, not only money, but kind of development and so on that you need for these things is gigantic, right? So early planning for these operations started in the 90s, and now we have a launch window in 2034. That's really all I want to say. Before I close it, let me throw a big shout out at folks in my group that work with me. These are the people I have the pleasure to work with, and it's a mixture of, and at least I try to assemble a team with both, I guess you call it domain knowledge and technical knowledge. Am I learning the right way of saying? So we've got folks saying, working on star clusters all the way to, again, backgrounds and signals and waveforms, which are the specific of black holes and so on, dark matter and so on. But then I try to go, surround myself with, PhD students in machine learning, statisticians. Rodrigo, who's an expert in data cleaning, he's actually been leading a Kaggle challenge on gravitational wave applied, pattern recognition and so on. So hopefully, domain knowledge and technical knowledge can go hand in hand. And that's all. Thank you.
Thank you so much. So we have got some questions for you. So first one is, on which scale can you predict the shape of a gravitational wave from the merger of a binary? What is the order of magnitude of precision you can achieve?
Well, it's order so it's order 1% below detection level. So detection level is 10 to the minus 21. We predicted up to 1% below that. And the reason is that we have a theory behind. So it's a field that is very, very heavily theory informed. So we have a specific theory, which is Einstein's general relativity, which has a super strong prediction on how our signal should look like. So this pattern recognition problem would be impossible for a unmodeled search. We do run unmodeled searches. That's to check if there's a gravitational wave signal that doesn't look like anything we've seen before. These things are done, but they're much less sensitive. In practice, right now, all the signals that we found are signals that we knew how they look for. And this is crucial because, again, we are fighting against orders of magnitude of noise. And it's like having a good model is like having a magnifying lens that lets you, increase the sensitivity of what you want to see. So we find what we are looking for, which is a limitation of our research field, I think.
Okay. So the next question is, why the time delay between gravitational wave event and the correlated electromagnetic events doesn't both travel at the speed of light?
That's very true. They both travel at the speed of light. Actually, maybe. That's a key prediction of Einstein's theory. So one way to test whether there are corrections on Einstein theory is testing whether photons and gravitational waves travel at the same speed. The initial time delay, it comes from the astrophysics, because the photons are trapped indeed. So when you merge two neutron stars, the density of what you produce is so high that photons cannot escape. It's like having a cloudy it's like having smoke in the room, right? So if I put smoke in the room, photons cannot, the way I see you in front of the room is because there's a photon that can travel from here to there. If there would be smoke, photons will just go around and I don't see things anymore. So the density in the neutron star is so high that photons are trapped at the beginning. Then the star expands, the density goes down, and photon starts free streaming, and this is what's causing that delay.
Oh, so I think, okay.
Thank you for the talk. Nice. Thank you very much. So one question, can you comment on the stack, technological stack that you use for multi-messenger astronomy? I mean, these packages, I think, first of all, they are Bayesian, so...
I'm a deep Bayesian, so...
But I think are for offline analysis, no? Mainly?
Both.
So you use Python also for real-time...
low latency.
Okay.
For low latency.
Without like C++ binding and this kind of things.
Oh, that's deep because I don't personally work on low latency pipeline, but surely, and that's the way I interact with these. All the interface it's done on Python. Yes.
Python.
Now
Okay.
we might have, and I'm actually not sure because it's not really my core expertise, but there might be some compiled things down the line. So yeah.
Okay, thank you very much.
Okay, you know. So Daniele here is a former gravitational wave physicist converted to software engineering. No, you told me machine learning engineer. Yeah. Sorry for the...
Well, nowadays it's called AI.
Okay, sure.
Okay, so I think no one has anybody has any questions? I don't see. Yeah.
Sure.
I'm sorry if I'm saying this, but probably you quoted the wrong movie by Nolan, because how come you didn't show anything about Inception? Because Interstellar, where they did like this massive. This is just a comment, just because I remember reading a technical paper.
Okay. I'll go there. Actually, Kip Thorne was one of the producers of Interstellar, right? Nobel Prize for gravitational wave physics. Now, I really disliked the movie. I didn't like it. So
what I wanted to say was that they published a paper that where they actually like outlined very detailed how they put together equations and these like fancy like graphic renderer to model how the black hole would be.
Yeah,
seen.
and I have a curiosity on this. So we run simulations of merging black holes all the time. The most expensive simulation of black holes that was ever run is the rendering of an Hollywood movie. Right? I mean, the kind of money that they have is immense, right? Compared to what we have in academia, right? So actually, the most CPU hours that went into black holes are for that image, not for Nobel Prize discoveries. But that's, yeah.
So then, we can take one last question if you guys want. Anyone interested? No? Okay, so so thank you guys for joining us.
Break.
Big round of applause for them.